Alright, let's talk about a concept that we know very well. It's called the temperature, or do we? And talk about the zero law of thermodynamics. So one thing to highlight here is the temperature is an interesting concept, and it is tricky. All right. Again, you may be saying, "What am I talking about here?" But we humans in general, we confuse heat transfer with temperature. We call things that has high heat transfer coefficient as, for instance, let me before going into definitions. So why don't I do this? So here, as you know, I'm in Florida, so it's fairly hot outside. Let me see actually the temperature right now. It is 91 Fahrenheit at this moment, right? So if I go to my car and if I touch the dashboard, and also with one hand, if I touch, let's say my seats are closed, especially if I touch it, wow, my hand on the dashboard is gonna hurt a lot, right? It's too hot. But the closed seats, not too bad, right? They are at the same temperature. The only thing that difference between those two is dashboard is an injection molded plastic, which, well, maybe covered to some other manufacturing things to look fancy, whatever. Basically, its heat transfer coefficient is higher than the seats. That's why you feel hotter. Okay, so that's why we are confusing it, and we usually associate it with that. And if you look at the temperatures, for instance, they give feels like. That also includes the heat transfer effect into your, how you feel it. Okay, so that's what I mean by temperature is a little tricky concept, right? But I mentioned this at the first video, but now I will be able to expand on it slightly more. There's not a lot to expand, but here's what it says. And I made a joke. I said that this is a Captain Obvious, law. But here's two thermodynamic systems. Let's say, and I have two systems. This is system A. This is system B, and they are in thermal equilibrium. Okay, so their temperature are the same. And I also have another over here, and I have a third one, right? C. And what I'm saying is, if B and C are in thermal equilibrium, as well as A and B are in thermal equilibrium, then I'm going to say that the temperature at A will be equal to temperature at B will be equal to temperature at the C. So again, this is gives some numbers to how hot we feel or how cold we feel. Okay, so it is important for us to have this. So this is like a baseline. And interestingly, actually, the first law and the second law has been found established before the zeroth law. So the zeroth law is after those two. But as this is a much more fundamental that we need for the first and the second law, we just simply put it as the zeroth law. All right. Okay. Nothing else I want to talk about in the zeroth law of thermodynamics. You know what I'm talking about here. Okay. The other thing I want to talk about here is the temperature scales, especially thermodynamic temperature scales. So I want to go ahead and draw basically a temperature gauge or a scale. And what I'm going to do is, let's say I have water over here, and I have boiling, and I have freezing right over here. Okay, here is my 0, freezing, and this is going to be the Celsius. Oops, it's going to be the Celsius scale. This will be the Fahrenheit scale, right? And the Fahrenheit scale, I have 32. I have 212. I have over here 100, right? I'm sure most of you know what I'm talking about so far, right? Okay, so now the interesting thing is this. We covered something called the state postulate. What did it say? It said that as long as I have two independent intensity properties defined, and I'm going to pick for this particular example as a container like this, air, and low pressure, low P air, let's call it that way, or gas, it doesn't have to be air. Okay, P is one of the properties over here, and I'm going to have the specific volume as well. So I know the volume of it, I know how much gas I put in it, so as long as that, I can find this guy, right? I can also measure my pressure, oops, right? So now I know this. So by the state postulate, I will be able to obtain all the rest of the properties because my state is known. So what does this mean? I can find my T. Okay, that's pretty cool. So let's do it. And when people did it, well, let's say that I just pick I don't know, some kind of temperature right here, and I pick I have to be a little careful over here. Let's say I pick this. Okay, from 2 points I can get a line, right? Well, okay, more interesting is this. I get this, I get this, I do a very different, pressure values corresponding to the temperature, and I get myself a really straight line, okay? Obviously with some error, and then I can go down in my pressure, but I cannot go to, zero. But if I extrapolate, okay, it's gonna hit it right over here. I didn't do a great job, but whatever, okay? This is where the pressure is zero. So okay, let's do the same test with another, like I do this, I do that, I do this, I do that, I do this, and then I plot this, and then I extrapolate. I'm sorry about, it goes to the exact same point, okay? So this point, the temperature in Celsius turns out to be minus 273.15 Celsius. Okay, that is kind of interesting. And then I can go back to here, to the Fahrenheit scale, and I actually obtain this to be minus 459.67 Fahrenheit is what I have for that very point where all the gases, and I can continue this analysis for different low pressure ideal gases, okay, and see at a sufficient low pressure, gases, we'll talk about that, act as ideal gas, so this will be quite legit, okay. And you can do additional, you always come to the same point. It's kind of interesting, right? And here's why the absolute zero temperature is defined, and we call this 0 Kelvin, okay? And we call this 0 Rankine, right? So this is how we obtain the different varieties, and you can see it looks like okay, right, 0 Kelvin, but I think you follow me. And if I go back over here, so this will be 273.15, this will be 373.15 in terms of the Kelvin, and you can make a similar arrangement for the here and here as well, looking at this relationship, right? So okay, some important observations that we will be needing in the rest of the course, because okay, note, definitely you will be converting things to Celsius, to Kelvin, Fahrenheit, to Rankine for sure, okay? So get to know these things. But let's write this in here. I have a temperature, and let's say that it's given in Kelvin, okay? You can see I have established over there that I have the temperature in Celsius plus 273 plus 15, isn't it? So, I mean, it's obviously here, right? So I have a Celsius like 0, I have 273.15, I got myself in the Kelvin. Same thing, similar arrangement can be made for the absolute temperature in the Fahrenheit Rankine scheme. So you get yourself and plus this time around 4, 5, 6, 7 Fahrenheit. Okay. Okay, that's good. Let's go another observation. Did you realize that these are on the same scale? So if I have subtract this value from this value, what do you get? 100. Subtract this value from this value, what do you get? 100. So this delta T, the temperature change, okay, in terms of the Kelvin scale, will be equal to delta T of the temperature change in the Celsius scale, okay? Again, exact same thing can be said for the Rankine versus the Fahrenheit scale, okay? And the fifth thing I want to talk about is how the temperature of the Rankine and temperature of the Kelvin is related. So you can see this is actually 1.8 times this, mathematically speaking. You can see that this temperature in the Rankine scale will be temperature of the something in the Kelvin, and I need to multiply this 1.8. Okay. So now actually, many of you know this. What's the relationship between Celsius and Fahrenheit? You multiply by 1.8 and you get 32. That's where the 1.8 is coming from. Okay. Okay, and actually let me just write what I said because it's kind of important. Temperature at the Fahrenheit scale will be equal to temperature at the Celsius scale, and I'm going to multiply by 1.8 plus 32. Why 32? You can see here, right here, right? This is where it's coming from. Okay, because that's going to be 0, right? I have to make sure it's just matches to what I have. So these observations that I have here, I can solve a question, but that's not going to really be very helpful. You should practice yourself. But this is what I have for the temperature side of things. Okay. Thank you for watching this video.